students, and welcome back to Study Room. So today we're going to be starting the chapter on electricity. So personally, this is one of my favorite chapters in physics because it's got a lot of application. It's a lot of hands-on work. Okay, so I hope you're going to enjoy this chapter doing it with me. Okay, so we're going to start the chapter on electricity. Now, what are the day-to-day, applications of electricity? Can any of you give me any guesses? Well, what you see right here in this picture, I'm sure all of you have seen these big Eiffel Tower like towers. These are nothing but electric towers, and these wires that are connecting and going in all directions, these are the wires that carry the electric current or the electricity that finally comes to your home. So it's so easy for you. You probably don't even think about it. You just switch on the fan, you switch on the light, you switch on the AC, you plug in your phone for charging. All of these things are possible only because of electricity. Okay, so these are some basic day-to-day applications that you must have seen everywhere around you. Okay, so it's also important that when, as a science student or as a student studying physics, even if you're saying oh, I don't want to do science later in life, still these are some things that are happening around you all the time. So if not anything else, you should be more aware of what is happening around you, what you are doing every day subconsciously, not even knowing what you're doing, right? So all of these things that I said, switching on the fan, switching on the light, plugging in your charger, all of these things are applications of electricity. You are using electricity for your day-to-day purposes, okay? Okay, so like I just told you some applications of electricity. Now we're going to see a short video in which it's going to become more clear exactly how much we use electricity in our day-to-day life. Okay. So we're going to see a lot of examples here. These lights that you light up, these solar panels generate electricity. These solar panels, what do? They basically use the energy from the sun and convert it into electricity. The bulb that lights up our homes, the whole city that is lit up so beautifully. All of this is what? It's because of electricity. Okay, so you should know how wide ranging the applications of electricity actually are and how much we use it in our day-to-day life. Okay, let's move on now. So can anyone tell me what is the common thing between these two? First, tell me what are these two images. The first one, this image, very clearly is what? Lightning, right? Everybody has seen lightning. Everybody has seen those quick flashes of bright white light, which is followed by what? Thunder, right? So that is lightning. And what is the second image? Can anyone tell me what the second image shows? You can see a nurse in the background, right? So it's pretty clear that it is in a hospital, right? So what is that machine which shows those lines? That is nothing but an electrocardiogram, okay? Or in short form, it is known as ECG. So basically, if a lot of you don't know about it, if you haven't studied it in your biology chapters yet, messages through our body is sent basically in forms of electric messages. The neurons, between the neurons, the messages are sent in the form of electricity or electric current. All that we're going to study in detail about, but I'm just giving you a brief. So your heart muscles basically contract or relax based on those electric signals that it receives. Okay, and this machine, the ECG or the electrocardiogram, basically measures those electric signals or those electric currents that your heart receives, and that is how these lines are formed. Like so they basically monitor those electric currents or electric messages or signals that your heart receives, and based on that the doctor tells you like what is your problem, what the problem is with your heart, or is your heart weak, or is your heart healthy. Okay, and the first one is nothing but lightning. Lightning is only a discharge of electric charges in the atmosphere. So you don't need to know too much about detail about that right now, but it's basically, it's all electric current, it's all electricity. So electricity is all around us, from our hospitals to the sky. Okay, so that is what is common between these two pictures, electric charge or electric current. Okay, moving on. Now, current. What is this? What is this picture have to do with our study on electricity and electric current? This is nothing but water current, right? So, what does water current have to do with electric current? Or, say, if I don't give you the example of water current, if I give you the example of air current, what does that have to do with electric current? Well, that is because the base of the meaning of current is same, be it air current or water current or electric current. And what is that meaning? Current is basically the movement of something, something's movement that gives rise to another phenomenon. So the water current gives rise to a river looking like this. Air current gives rise to the winds, and electric current is basically the movement of electric charges. So I just told you that electric current is caused due to the movement of something. Water current, what is it caused by? The movement of? Of the water, right? What is air current caused by? The movement of the air. And what is electric current caused by the movement of? It is caused by the movement of electric charges. So if I just write it here for you, current is nothing but the movement. Basically, it is defined by movement. Okay. So like water currents are movement of water. Air currents is the movement of air. And similarly, electric current, which we are going to currently deal with, is the movement of electric charge. Okay. Now let us see in a little more detail what exactly electric current is. So what is electric current? Let's first read in your PPT and then I'll explain it to you. So electric current is expressed by the amount of charge. I'm just going to underline the important things. The amount of charge flowing through a particular area in unit time. Okay. It is the rate of flow of electric charges. Now, what is an electric charge? You might ask me, we don't know what electric charge means. So for this, I'm going to have to tell you that there are neutral particles and there are charged particles. Neutral basically means it doesn't have any positive or negative charges. And charged particles, I'm sure you've learned about static electricity. When you were small kids, you must have learned that when you rub a scale against your hair and then you take it near a small bit of paper, it basically attracts it, right? Why does that happen? Because when you rub the scale against your hair, that scale develops certain charges. And then that charge that the scale develops attracts those small bits of paper. Okay, so now you're going to have to keep those concepts in mind for this chapter. So charge is basically a positive or a negative charge that is developed on a body due to any reason. Like for it could be due to like the rubbing of the scale or any other reason, like static charge or static electricity. You must have noticed like when it's cold, when you're like removing your sweater, you just feel like little pops of electricity on your arm, or you just touch someone and it instantly feels like they give you a small shock. That is static charge, because of which is static electricity. So what is charge? Charge is nothing but those ions. I'm going to use the word ions. Basically, ions are the positive and negative charged particles. So you could just say charged particles. So charges are the charged particles. They're not neutral. They're charged particles that flow. Okay, so when a charge flows, like I just told you, what is water current? It is because of the flow of the water droplets of water. And what is electric current? It is because of the flow of these charges. So the charge can be negative and the charge can be positive. Okay. So now what is electric current defined as? We define electric current by the amount of charge. Like if I say, we define charge by the symbol Q. Capital Q is for charge. Small t is for time. And current, we always use the symbol I for current. And what is the unit of current? Like we say that, what is the unit of distance that we generally use? What do we say? That like the scale is some 15 centimeters, right? So we use the unit centimeters for distance. Similarly, the unit that we use for charge is ampere, which is denoted by, we don't write the full word ampere, we denote it by A. So this is the unit. Don't get confused between what is the symbol and what is the unit. Okay, symbol is what we use to denote it in an equation. Unit is what we finally put at the end of it. Like we write 3 centimeters or 6 centimeters or 5 kg. These things are units. And these Q, T, I, this is what we use to denote a particular quantity. These are known as symbols. Okay, so these two things should be clear to you. Okay, so this is what you have to keep in mind right now, that electric current, I just told you that electric current is the flow of something, right? So what it is the flow of? It is the flow of charges. So how we define it is the flow of charge in a particular area in unit time. In unit time basically means, unit means 1, and time, what is time, is measured in seconds, right? So unit time means per second. So another way you can write unit time is per second. Okay, this is how you can write unit time. So how we express it, we'll do it in a few slides. Okay, let's move on from here. Keep the concepts of unit and symbols in mind. Okay, so now that we know the concepts of symbol and unit, I'm going to tell you one more thing, that the direction of current, we have to look at this red line. Okay, so one thing that you have to keep in mind is the negative charges. The negative charge is what goes from the negative terminal of the battery to the positive terminal. Okay, so look, this is the battery. So this battery has a negative terminal and a positive terminal. Okay, if you find all of this a little confusing right now, don't worry, we are going to study some more concepts later on in this chapter that will make these concepts even more clearer for you. Okay, so just keep this in mind, that the battery has a negative terminal and a positive terminal, or a negative side and a positive side. So from the negative side, the negative charges flow out like this. Obviously, the negative charges flow like this, right? Negative, negative. Obviously, the negative charges go from the negative terminal to the positive terminal. And by convention, like that is what is done usually, it's just what is universally accepted, is that we take the flow of electric current in the direction opposite to the flow of negative electric charges. Okay. So, if we say the negative charge are also known as electrons, and the positive charges are also known as protons. This is an additional information I am giving you right now. So, if the negative charges or electrons are flowing in this direction that I have drawn right now, just forget the figure and the arrows drawn in the figure for a moment. Okay, so if the negative charges are going like this, or they are going clockwise, then we just say that by convention, direction of current or electric current is opposite, I'm writing in short form, to direction of flow of negative charges or electrons. So basically, now who can tell me, if electrons are flowing like this in this direction, then what would be the flow of current? Like we just said that by convention it is taken opposite. So that means current would be flowing in this direction, like this. So basically, the negative charges go from the negative terminal of the battery to the positive. Obviously, the negative charges would leave from the negative terminal only, right? And this is what you have to remember, that by convention, the flow of current is taken as opposite to the flow of negative electric charges or electrons. So current flows in this direction. So the second arrow that I have drawn is for current. Okay. So now I'll show you one short video also. Okay. Let's see what is happening here. You can see there is a battery, right? The battery has one positive terminal which is on the upper side here, one negative terminal, this one on the bottom. You can see the plus and minus sign, and these blue spheres, if you look very closely, they have these small minus sign on them. If you can see in white, they have this small minus sign on them. Can you see that? Can you see inside these blue spheres there is this small minus sign? What does that mean? That these blue spheres are negatively charged or are negative charges or electrons, right? So where are the electrons going? Now look at the flow of electrons. Where are they going? Are they going from the negative terminal to the positive or positive to negative? They are going from the negative terminal to the positive terminal, right? So that is what happens. The electrons or the negative charges go from the negative terminal to the positive terminal, and electricity by convention flows from the positive terminal, or electric current flows from the positive terminal to the negative terminal. Okay, moving on. So what have we learned right now? That we have learned that the negative charges go from the negative terminal of the battery to the positive, and the current flows in the direction of the opposite direction of the flow of electrons, which means that current goes from positive terminal of the battery to the negative, which means you can say either that electric current flows opposite to the direction of the negative charges, or current flows in the same direction as the charge of positive charges, direction of positive charges, right? The positive charges obviously go from the positive end of the terminal of the battery to the negative end. So electric current goes in the same direction as the positive charges. You can remember this because we should all be positive. So we should all go in the direction of positive. So current does the same thing. It goes in the direction of the positive charges. And obviously positive charges go from positive terminal of the battery to negative terminal. Okay. Okay, moving on. What is an electric circuit? So we just studied the concept of electric current, right? Now we're going to study what a circuit is. So basically, the circuit is a continuous. So I'm going to circle the important words here, okay? It is a continuous and a closed path of an electric current, okay? Now what does continuous mean? Continuous means that it has to be in one straight line. It has to go, keep going. It should not break in the middle. Like if it's like this, current cannot flow here. Current can only flow if the circuit is continuous or it is in a line which is going on continuously. Like look at this. This is a battery. Okay, the representation, how we represent a battery, like these small and big lines, we are all going to do all that. So right now you just need to know that this is the positive terminal of the battery is always represented as a long line and the negative is represented as a small line. So this basically makes up a cell. Okay, a battery is made up of cells. So you can either represent a battery with just these two lines, or you can show it as two sets of these lines, like a positive terminal, a negative terminal, another positive and another negative. So this is basically two cells you are showing. Either of these representations is acceptable. You don't always need to show like 2 or 3 sets of cells. That's like every book does it in a different way. Okay, all you need to know is the longer line is the positive terminal. So here it is written positive, and the shorter line, this is the shorter line, this is the longer line. The shorter one is negative. It's written negative here. So we know that the electrons, where do the electrons flow from? Negative of the terminal to the positive or positive to negative? Electrons, they're negative, so they come out of the negative terminal. So this is the electron flow. And we know that the electricity or electric current flows in a direction opposite to that of electron flow, right? So electric current goes from the positive terminal of the battery to the negative. So here you can see this. These arrows that are drawn, they are coming out from the positive terminal, right? They're going from the positive terminal to the negative terminal. So this path, this line path, is basically what a circuit is. Can you see that this circuit is continuous? Like there is no break anywhere, right? So that means continuous, and closed basically means that there can't be any, like if there is a switch here, if this switch is removed. So the circuit is open. Current cannot flow in an open circuit. By continuous and closed mean almost the same thing, but they're used as two different words to define a circuit more properly. So continuous also means that it shouldn't have any breaks in the middle, and closed basically means it shouldn't have any open places. It can't be like one wire is here and one wire is here. Those two wires have to be connected. Like here you can see, if this part is wire 1, this part is wire 2, this part is wire 3, and this part is wire 4, right? So all these 4 wires are supposed to be connected. They can't be disconnected anywhere. If this 1 and 2 are disconnected here, will current flow? Current will not flow. So a closed and continuous path for electric current is known as an electric circuit. Okay, great. Moving on. The formula and unit of electric current. So if you remember, we just did the definition of electric current. What is electric current? How is it defined? It is defined as the flow of electric charges in a particular area per unit time, right? So now we're going to use that exact definition to calculate or to derive the formula of electric current. Now, for net charge, I just told you there also, charge, the symbol for charge is Q. Okay? So the net charge flowing across any cross section of a conductor in time t. So if the Q is the charge flowing through any cross section basically means any small part of the wire. Okay, the wire is what makes up the circuit. You remember the lines that I told you that I marked 1, 2, 3, 4. Those lines basically are the wires that are used for connecting the different components. So if you go back to that circuit, you will see a battery which has a positive and negative terminal. You will see a bulb which basically lights up when there is current flowing in the circuit, right? There is a K. The K named component is the key. So key is basically something that can be used to break or make the circuit. So a key is nothing but it is basically, there is this metal piece that is kept there, and if this small piece is inserted into the key, electricity can flow through it, and if that small piece is removed, electricity cannot. It can also be considered a switch. So if the switch is closed, current will flow, and if the switch is open, current will not flow, because current needs a closed and continuous path, right? So coming back to this, any cross sections mean any part of the wire of a conductor in time t. I told you that for time we use the small letter t, and current I told you current we use capital I through a cross section is given by I is equal to Q by T. So you remember we said that the current is defined as the flow of electric charge per unit time. So we say, if you use the definition, current I is the flow of charge. Charge means Q. Flow of charge per unit time. So by per unit, for whenever we say per unit centimeter or per unit length or per unit time, that always means divided by that quantity. So if we are saying per unit time, it means divided by time. So here we have the formula of current. So if you do not remember the formula per se, you can go back to the definition of current and then you can derive the formula from there. You can say, okay, it's charge flowing through an area per unit time. So charge and time. We don't need the area here. So charge per unit time is current. Okay. The SI unit. So SI basically means the standard unit of electric charge is Coulomb. Now this is the unit that we're talking about. Okay. So if I have to make a table here, unit, first we'll write the symbol. If you have to make a table here for like symbol and unit. So these are two important things that you have to remember. Okay. So, and this is the quantity. What quantity are we talking about? So if we say it's charge, the symbol for charge we just said is Q and the unit is Coulomb. C-O-U-L-U-M-B. And Coulomb is just represented by C. Like a short form for the unit of charge Coulomb is C. Next thing is current. The symbol for current is, what is it? I, and the unit is ampere. or it is represented in short form by capital A. Then time, what is the symbol for time? It is small t, and unit we always have been referring to time in seconds or small s. Okay, so these are the things that you have to remember, like what is the symbol and what is the unit. Okay, so we can say that 1 coulomb of charge is charge contained in nearly 6 into 10 to the power 18 electrons. This is just for you to remember per se. This is nothing that you have studied about. This is just a fact. Okay, and the SI unit of electric current is ampere, that we know. Another thing that you need to know about is this ampere can be used in many ways, like it can be milliampere, microampere. What does that mean? Basically, milli means any number into 10 to the power minus 3. Like you know the conversion of millimeter into meter. How do we do it? Millimeter to meter. When we have to convert millimeter to meter, we divide it by 10 to the power 3 or by 1000, right? And if we have to do the other way around, if we have to convert meter to millimeter, we multiply by 1000, right? So in the same way, if we have to convert milliampere into ampere, we just do, if it is 5 milliampere, so it is nothing but this milli, the small m for milli is replaced by the division by 1000, right? So if it is 5 upon 1000 amperes, this milli has been used here. So this 1000, if you have learned how to represent it exponentially, is 10 to the power 3, because it's 3 zeros, so it's represented by 10 to the power 3. And when we take this to the numerator, this 3 basically becomes minus 3. This becomes a negative sign. So it's 5 into 10 to the power minus 3 ampere. Okay. Similarly, micro is 10 to the power minus 6. So you don't need to know about that right now, but milli is a very common conversion because you've learnt about millimeter and centimeter to millimeter to centimeter conversion, millimeter to meter conversion. So it's like that only, like millimeter to meter, you go 10 to the power minus 3. Similarly, milliampere to ampere, you multiply by 10 to the power minus 3. Okay. Now, ammeter is nothing but a device that is used for measuring the electric current in a circuit. Okay. Measuring instrument that is used to measure the current. Okay, so if you connect an ammeter, go back to that circuit that we just studied about with the bulb and the key and the battery. If you connect an ammeter in that circuit, that ammeter will basically tell you how many amperes of current is flowing in that circuit. Okay, so it's basically used to measure the current, and you can see here that here in this diagram, you can see that there is an A symbol drawn. That A is nothing but the unit of current, which is ampere. Okay, great. Now, what is drift of an electron? We know, let's first read in your PPT and then I'll explain it to you. So it says that current cannot start only when an electron from one terminal of the electric supply physically reaches the other terminal through the bulb, because the physical drift of electrons in the conducting wire is a very slow process. Okay. And that the exact mechanism of current flow takes place with the speed close to the speed of light. So you remember when we did the speed of light, we defined it as 3 into 10 to the power 8 meter per second. So if we just think about the drift of an electron, the drift is a super slow process. So you must have noticed that as soon as you switch on the light, as soon as you just turn on the switch, the light lights up, right? You don't have to just stand there and wait for the light to light up. It's an instant process. So that doesn't happen because the electron goes slowly from like one end of the circuit to the other. That's not how electricity flows. Electricity is not only because when one electron reaches the other end. It's not each individual electrons reaching the other end. It's the electricity flowing as a whole. So you just need to know that electricity flows at a very high speed, and it is not because of each individual electron starting from the negative terminal and going to the positive terminal. It's a continuous process that takes place like this, almost equal to the speed of light. Okay. Moving on, we're going to do some questions. So this example says that a current of 0.5 ampere is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. Okay, great. So always when we start an answer, we write the given quantities. So we write given, and with given we always write the symbols because we define the formula in terms of the symbols, right? So we are given that the current, what is the symbol for current? It is I, is given as 0.5 ampere. What is this 10 minutes? That is time, right? So time T is given by 10 minutes. So now we know that this 10 minutes or minutes is not the standard way of, like, standard symbol for or standard unit for time, right? What is the standard unit for time? It is seconds. So we need to convert this minutes into seconds. We know that time doesn't have the standard units minutes. You remember what was the standard unit for time? It was seconds, right? So we need to first convert this minutes into seconds. So 1 minute has how many seconds? It has 60 seconds. So 10 minutes basically has 10 into 60 seconds. And 10 into 60 is what? 600. Okay. 1 minute has 60 seconds. That means 1 into 60. And 10 minutes has 10 into 60 or 600 seconds. Next thing, what do we have to find? We have to find the charge. Unit for charge? Not unit. I said it wrong. Don't get confused between unit and symbol. Symbol for charge is Q. We have to find it. So we write the formula. I is equal to Q upon T. So Q is, what is Q? We take T to this side. It is I into T. Now we put the values of whatever we know here. Current we know 0.5 ampere into time we know as 600 seconds. Right? So this 0 removes this decimal of 5 and 5 6 we know 30 and this extra 0 300 Coulomb. Now we are going to use the unit of charge. So 300 Coulomb is the answer. Okay, moving on to the next question. So the next question says, what does an electric circuit mean? So we've studied that the electric circuit is, what were the two important words here when defining an electric circuit? Continuous and closed. Right? So an electric circuit is a continuous and closed path for the flow of electric current. Right? If there are any breaks in the circuit, if it's discontinuous or if it is not closed, say the switch is open, in both the cases current will not flow. So it's important for the circuit to be continuous as well as closed. Okay. The next question says, define the unit of current. So what is the unit of current? Unit of current is ampere. So when they say define the unit, so you remember that in the last chapter we studied that whenever we have to define a unit, we take everything as 1. So if the current is nothing but Q upon T, then we take Q as 1 and T as 1, so that 1 divided by 1 is 1. Our current also comes out to be 1. So we are able to define 1 ampere or 1 unit of current, which is 1 ampere, which is the standard definition, right? So say if we take the charge as 1 and time as 1, how will we define it? We will say that 1 ampere, because the answer will come out to be 1, charge is 1 and time is 1. And current is charge upon time, so 1 divided by 1 is 1. So 1 ampere is the current. And here this is how we define the unit of current, because the unit of current is ampere. So 1 ampere is the current that is given rise to, or it is generated, you can write anyway, is given rise to when what happens? How many units of charges? One, right? When one unit of charge, if it's better, what is better than writing 1 unit of charge? We know the unit of charge. What is the unit of charge? It is coulomb. So when 1 coulomb of charge. Now, to continue, we go back to the definition that current is defined as the charge that flows through a particular area in unit time, right? So here there is no mention of area, so we write it as it is. So when 1 coulomb of charge flows through a particular area, in how much time? In 10 seconds time? 20 seconds time? No, right? In 1 second time, or which is known as unit time. Particular area in unit time. Or even if you write in 1 second or per second, that is fine. That will also be acceptable. So 1 ampere is the current that is generated, or current that is given rise to when 1 coulomb of charge flows through a particular area in unit time, or 1 second of time. Okay. Now, the next question says, calculate the number of electrons constituting 1 coulomb of charge. So for this question, I'm going to tell you a new formula that you will be learning. Okay. So the formula goes Q. So the formula goes like this. Q is equal to NE. Okay. So here this Q is also, it can be written as capital Q. This is the charge, is equal to N into E. Here N is the number of electrons and this E is the charge on the electron. This is an extra question. This might not be asked in your exam per se, but this is something that you should just know as an extra knowledge. Okay. So this N is the number of electrons and E is the charge on an electron. So we write, if we want to find out the number of electrons, how do we write this formula? N equal to Q upon E, right? And we are given Q as 1 coulomb of charge. So Q is 1 coulomb. And we know this is something that you need to know. You also learn this in later classes. But this is something that you need to remember, that this charge on 1 electron is nothing but 1.6 into 10 to the power minus 19. Okay, this is the charge on an electron. So if we solve this, so we have to basically find N, which is 1 upon 1.6 into 10 to the power minus 19. Okay, so if you want to divide this, if you take 19 to the numerator, it will become into 10 to the power plus 19, right? And if you want to remove this decimal, I have to add a 0 here. So this becomes 10 upon 16. This cancels out. How many? By 2, if we go 2 5s are 10, 2 8s are 16. Then N is equal to, what is 5 by 8? 0.10. 8 5s are 40. 8 6 are 48, right? So approximately 0.6. So if I want to solve it for you, I'll just solve here. If it is 5 divided by 8, right? If we have to do 5 divided by 8, right? So if we have to do 0 point, so 50, 5, 8 5s are, 8 5s are 48. There is a 2 here because we've added a decimal, so 0. Then 8 2s are 16. We have a 4 here, 0. So 8 5s are 40, right? So we get a 40 and a 0. So this becomes basically 0.625 into this 10 to the power minus 19, which we've talked up to the numerator. So it's 10 to the power 19. So if we have to write it in standard form, this would be 6.25. What did I just do? I took this decimal and took it to this place, right? I took it one side to the right. So if I have to write it here, it would be 10 to the power minus 1, right? So that this decimal, because of this minus 1, it goes one place back. So this is 6.25 into 10 to the power minus 1 into 10 to the power 19. So this becomes, this 19 minus 1, it becomes 6.25 into 10 to the power 18. So that is the number of electrons in 1 coulomb of charge. Okay. So in this video, what did we learn? We learned about electric current, what is electric charge, which direction does the negative charge flow in, and electric current flows in the opposite direction of the negative charge. We learned about the circuit, we learned about the formula of electric current, and we did a few numericals. Okay, so make sure all of these topics are thorough with you, because moving on, all of these topics, each and every single one of the topics that we did today, be it the circuit, be it current, everything is going to be used in the further topics. Okay, so come prepared, take care, and thank you. I hope you enjoyed studying.